Okay, I wanted to give you a quick example of how we can use relative motion in a calculation. In this case, we've got two people. Someone is in a canoe floating down the river, and or actually they're sailing down the river, canoeing, and another person standing on the bank. Okay, so first of all, we have a man in a canoe who's canoeing down the river. Uh, um, the river flows south at 2.5 meters per second. The canoe moves at 7 meters per second relative to the water, directed at an angle of 25 degrees east of south. So the river is flowing south. The person is going east across the river, but not directly across the river. They're going south east. And the river is 50 meters from east to west bank. And so the width of the river is 50 meters. So this river flows south. The width of the river is 50 meters across, and this person is in a canoe going from going southeast across the river. We've got three questions to answer. How long will it take the canoe to travel from the west bank to the east bank? Second, how far south will the canoe be when it reaches the east bank? And third, what is the canoe's speed and direction relative to someone standing on the bank of the river? In other words, what's their speed and direction relative to the earth? Take a moment, pause the video, see if you can solve the problem, then come back and I'll show you my solution. Okay, let me show you my solution if I can. I drew a picture, and here's my picture to start off with. We've got the river banks here. The person starts on the west bank. They're going to travel to the east bank, but they're not traveling directly across. They're traveling at this angle. I've drawn this arrow to represent their velocity relative to the water. Relative to the water. So that's 7 meters per second, directed at 25 degrees east of south. So I went south, go 25 degrees east of south. That's the direction I drew my 7 meter per second arrow. And I've labeled that arrow velocity of the canoe with respect to the water. So VCW, velocity of the canoe with respect to the water. That represents 7 meters per second. And I've labeled the angle here theta. That represents 25 degrees east of south. I've also drawn the speed of the river. We know the river is flowing directly south, so I just drew a blue arrow directly south, and I've labeled the velocity of the water with respect to the earth. Because this is how the water is flowing across the earth, then this 2.5 meters per second is the velocity of the water in the earth's frame of reference. Or in other words, in the frame of reference of somebody standing on the shore looking at the water, they would see the water flowing south at 2.5 meters per second. So I've drawn that arrow. Now, importantly, we've got a velocity in the Earth's frame of reference. We've got a velocity in the frame of reference of the water. And then I've got this distance, which I've labeled as L, 50 meters across the water. That's how we want the canoe to move relative to the earth. We want them to actually move this 50 meters across the earth. So in order to find things out, what is actually happening with the canoe, we're going to need to find out what the canoe's velocity is in the earth's frame of reference. In other words, in the frame of reference of somebody standing on the riverbank, not in the frame of reference of somebody in the canoe or in the frame of reference of somebody in the water. We've got their speed and direction relative to somebody floating along in the water. If you were in an inner tube floating down the river, you would see the person in the canoe moving away from you in this direction. But we want to know what the person standing on the riverbank would see. in order to be able to solve this. So let's think about this. This boat is, as this person is moving across the water in this direction, the water is also moving them downwards in this direction, south. So they're not going to follow this orange arrow in the frame of reference of the person on the riverbank. In other words, in the Earth's frame of reference. As they move in this direction, the water is going to move down. As they move more in that direction, the water is going to move them down further. And they're moving sort of along a line in this direction. If we were to draw that, what would that look like? That would look something like this. I've got the velocity of the canoe, or the motion of the canoe, relative to the water, but then if I add to that the motion of the water itself, I get the motion of the canoe relative to the Earth going in this direction, as we said. So what we've got to work out is the sum of these two vectors to get this vector. Written out in symbolic form, we could have the velocity of the canoe with respect to the Earth being the velocity of the canoe with respect to the water plus the velocity of the water with respect to the Earth. But we can't just add 2.5 meters per second to 7 meters per second, because again, they're not going in, that's not straight, they're not all in the same, a straight line. We're going to have to find components. Okay. Now, we want to find out how long it takes to get across the riverbank. And so if we were to think about what are the components here, well, we can find the components of the velocity of the water, the canoe with respect to the water, right? So I'm going to call this eastward component the x direction. And that would be the component moving the boat east. And then there's the component moving the boat south. And then there's the component of the velocity of the water, which has only a component south. The component of the velocity of the water eastward is 0. So the water only moves the boat southward. It doesn't move the boat across the river. Oh, and that's actually really useful because I want to find out how long it takes the boat to get across the river. Then all I need is this x component, this eastward component of the canoe's velocity with respect to the water, because I'm going to add to that 0. So the motion across the Earth, this 50-meter distance, that would be the velocity of the canoe with respect to the Earth in this eastward direction, times the time that it takes to go there. But this component, the component of this red arrow, velocity of the canoe with respect to the Earth, in this x direction, this eastward direction, is only going to be the component of the velocity of the canoe with respect to the water, this 7 meters per second, but only the part that's in eastward direction. So I'm going to have to work that out. In other words, if I looked at this angle over here, my picture over here, I want to find this eastward component. So that would be the opposite side of the right triangle. So I could take 7 meters per second multiplied by sine of 25 degrees. And that would give me my eastward component, this opposite side of my right triangle, this x component. And that ends up being 2.96 meters per second. So 50 meters is equal to 2.96 meters per second times the time it takes to get across the river, which means if I rearrange this, I can find out the time it takes to get across the river. That's 50 meters divided by 7 meters per second times sine of 25 degrees. Putting all that together, I got 16.9 seconds. So it's going to take this person 16.9 seconds to get across the river. Importantly, we didn't have to find the full velocity yet. All we needed was the part of the velocity, both velocities, the part of both velocities that moves us in this eastward direction. One of those components was 0, so it ended up being only the eastward component of one of my velocities that I needed. Okay, what about the second part? Well, to find out how far south we're going, we now know how long it takes. We're going to travel for 16.9 seconds. We're traveling 16.9 seconds. If we knew how fast we were moving southward, then we could work out how far we move southward. I've labeled that capital D. And to write it out symbolically, then capital D is going to be the component of my velocity with respect to the Earth. This full distance here, or full velocity vector here, times the time I worked out, 16.9 seconds. Well, this component in the y direction is going to be the y component of my canoe's velocity with respect to the water, plus the y component of the velocity of the water with respect to the Earth, which is just all of the water's velocity since it's only going south. So this is 2.5 meters per second. This is, well, I've got to work it out. That's the adjacent side of my triangle. So I want to take 7 meters per second times cosine of 25 degrees. This is 7 meters per second times cosine of 25 degrees. This is 2.5 meters per second. When I put those together, I got 8.84 meters per second. And then if I plug that in, here we go. Here's the full math. If I plug that in, I got 149.48 meters. That is to say, when I took that 8.84 meters per second, multiplied it by 16.9 seconds, I got 149.48 meters. Good. So to find how far we went south, we had to figure out the southward components of both of our vectors, and then add them up to find our total velocity in this southward direction. Multiply that by our time, and that got us our overall distance we traveled in the southward direction. Okay, now we can put everything together. We know how fast we're moving eastward. We've worked out how fast we're moving southward. And so we can already work out what the total speed is, i.e. what's the magnitude of our velocity. That's just going to be, here you can see we've got the southward component. Here we've got the eastward component. We've got a right triangle. So southward squared plus eastward squared, take the square root. And I got 9.32 meters per second as my overall speed for the canoe relative to the riverbank. So if somebody's standing on the riverbank, they would measure the canoe moving at 9.32 meters per second. And then to figure out the angle, the direction they're moving, I did the direction east of south, just like the first velocity vector was given. So I've labeled that phi. And to calculate what phi is, well, I can go tangent of phi is opposite over adjacent. So taking the tangent inverse of 2.96 meters per second divided by 8.84 meters per second. That ratio, take the tangent inverse of that ratio, and I got 18.49 degrees east of south. Just as a quick sanity check, we can think, well, if the water is pushing me faster southward, then I would expect my overall speed to be larger than either the speed of the water or the speed of my canoe relative to the water. And sure enough, 9.32 is larger than 7 meters per second, and it's also larger than 2.5 meters per second. So that's reasonable. And then if the water is pushing me more south, I would expect this angle to get smaller, as you can see in my picture. And so I'd expect phi to be smaller than theta. And sure enough, 18.5 degrees is less than 25 degrees. So I don't think I've done any errors in my math. And there we go. We've now worked out what the overall speed and direction of this canoe is relative as measured by someone standing on the riverbank. So using ideas of relative motion, figuring out what frame of reference each of our values was given in, and then working out what frame of reference we needed to be in to perform a certain calculation, we could figure out how long it took us to cross the river. It took 16.9 seconds. How far south we end up traveling as we cross the river. It ends up being about 150 meters. And we were also able to work out the overall speed and direction someone standing on the riverbank would measure us traveling, or the canoe traveling. It ends up being about 9 meters per second at 18.5 degrees east of south. Okay. Hopefully this is giving you some example understanding of how to deal with relative motion calculations like this. If you have any questions, please come talk to me.